Good morning, friends. Today we are looking the two-layer neural network and how the feed-forward and backward propagation works or tasks that happen in between the neural networks. So here it shows the single layer, hidden layer neural network. There is the input layer, hidden layer, and the output layers. So in the input layer there is A1, A2, and A2s are my inputs, and zeros is nothing but the position of that layer. That layer again connected to the hidden layer using the weights, and the weights W10, W20, and the 0 is nothing but the weight in between the input layer to hidden layer, and the 1 and 0s are is showing the nodes. Those are connected between the input layer and output layers. So by using of these W weights and the inputs, we calculate the Z1. This Z1 with respect to the 1 is indicating the first layer of the hidden layer neural networks. Z1 calculate by using of the W and the inputs. That Z1, once you calculate, pass it to the activation functions, and it's become A1 of 1. Again that hidden layers output A1 of 1, pass it to the forwarded to the output layer, that is the Z1 of 2, and using of the activation function it's become A1 of 2. This is the same as the y hat. So this y hat is nothing but my predicted values, and we compare that predicted value with the actual value, whatever the target value, and calculate the mean square error. And as per the as per the mean square error is high, so we have to update the weights to calculate accurate predicted values. So for that purpose we are also going to perform the backward propagation, and the backward propagation happen in between output layer to hidden layer and output layer to the input layers. Okay, so we go ahead to procedure for the feed forward neural network. The first step, calculate the Z1 from the input layer to the hidden layer. So equation is Z1 is equal to W naught into A naught, and whatever the Z1 we calculated, that pass it to the activation function. The activation function may be anything: ReLU, linear, sigmoid, bipolar, unipolar, sigmoid, likewise. Okay, so it can be anything. So as per the activation function, you will get the output. After the first step, we calculate the second step, that is the Z2, and again the equation W1 into A1. Okay, so again that Z of 2 is again applied to the activation function, and this gives me the A of 2, that is equal to y hat. Okay, that is the predicted output. Y hat is your predicted output, and after the once you got the predicted output, we calculate the mean square error is equal to half of t minus y square. Okay, so that is the calculation of the two layer neural network. And for the forward pass, now we are looking the backward pass, the step 4, that is the output layer to hidden layer, and with derivative of error with respect to W we calculated, and this two part is nothing but my dynamic part, and this one is my static part. Okay, so it gives me we just simplify that derivative, and it gives me A1 of 2 minus t into derivative of F2 of z into A1 of 1. Okay, and again we just update the weight value by using of the W new is equal to W old minus alpha E del E of 1. Okay, step 4, we are again doing the back propagation between output layer to the input layer, and this is what the derivative of the output layer to input layer. Just simplify that, and it gives me del E of 0 is equal to A1 of 2 minus t, derivative of the F2 of z, Wi1, derivative of F1 of z into ai of 0, and that del E naught, again we are going to update it by using of the same equation of the W new is equal to W naught of old minus alpha del E 0. Okay, so that the procedure we are going to use to calculate to what your two layer neural network, input layer and the output layer. These are my two layers. Okay, going ahead with the some numerical values. Here we are using x, that is a 3 cross 3, and w naught is a 2 cross 3, and t 1 minus 1 as per the number of 3 inputs. So 3 targeted values are there. F1 of z, taking ReLU activation function. F2 of z, we are using bipolar activation functions. And okay, w1 given 1, 0.5 and 0, and alpha is 0.1 is my learning rate. Question is draw architecture of neural network and find out the output after the one epochs. Okay, to calculate the one epochs we are using, we have to use 3 inputs one by one, and at the time of we have to update the w0 and w1 both the weights after the one iterations. Okay, so 3 iterations we have to use, and each iterations we have to use another one sample with respect to their targeted values. So right now we are going to start the first iterations by selecting the input 0, 1 and minus 1, and the target is equal to 1. Step 1, calculate Z1, that is equal to W0 into A1. So W0 is 1, 0, 1, 1, 1, minus 1, and A0 is 0, 1, minus 1. So here is the 3 column and 3 rows are available. So because of that, we are not going to add any bias term in A1. And by calculating this, we use minus 1 and 2. That Z1 we are applied to the ReLU activation function, and it gives me the output 0 and 2, and it's become A of 1. Next step 2, we calculate the Z2, and that is equal to W1 into A of 1. W1 is 0.50, and A, here we are added one bias 1 0 2 because number of columns are here 3 and number of rows available only 2. So that is a mismatch, and because of that mismatch we just added one here as a bias. Okay, and after the calculating of this, it gives me the 1, and that 1 we pass it to the bipolar sigmoid activation function. The equation for the bipolar sigmoid activation function is 1 minus e raised to minus divided by 1 plus e raised to minus 1 is equal to 0.462. So this is what my feed forward neural network. Now we are going to calculate the loss value and then backward propagation. So to calculate the loss value, the equation is 1 by 2 t minus y whole bracket square. So t is my 1 and y is 0.462. After the calculating, it gives me 0.144. Now again, after calculating the mean square error, we just go ahead for the back propagation. Step 4, that is output layer to the hidden layer. We calculate the del E of 1, that is equation A1 of 2 minus t, F1 of 2 of derivative of F2 of z into A1 of 1. So A1 of 2 is 0.462, t is 1, so minus 1. Derivative of Fz of 2 is 0.456 after derivative. The equation for the derivative 2, my derivative of 2 is a bipolar sigmoid. The equation is what? 1 by 2 in bracket 1 minus f of x square. So that equations we are use it for to calculation of derivative of the bipolar sigmoid, and it gives me 0.456 into now a1 of 1 0 1 minus 1 and transpose of that. By calculating of this, it gives me minus 0.245, and that multiply with the 0 1 and minus 1, it gives me 0 minus 0.25 and 0.245. Okay, so f2 of z is what? 1 by 2 minus in bracket 1 minus f of z square. F of z is 0.46 and it gives me 0.456, that I am written here. Okay, and it gives me the del E of 1 equal to bracket 0 minus 0.245 0.245. And now we are going to update the weight value. The equation w1 of new is equal to w1 of old minus alpha del E of 1. So old value 1 0.50 minus alpha 0.1 minus into 0 minus 0.25 minus into 0.25. First you just doing that operations, and that 1 minus with respect to that, so it gives me 1 0.5245 minus 0.245. Okay, so that is of step number 4. Next we again go ahead for the back propagation of the input output layer towards the input layer. The equation is what? A1 of del E of 0 is equal to A1 of 2 minus T F2 of Z, F2 derivative of F2 of Z, Wij, that is weight values, and W1 of Z, derivative of the W1 of Z, and A naught. Okay, so here at the time of the calculation we have to exclude the bias. Okay, when we are excluding the bias, then we are going to match the new output easily. F1 of Z is nothing but the derivative of the ReLU activation function, and it is a 1 when it's greater than zeros. Okay, for that purpose here this F1 of Z is always 1 for the if the output is greater than 1 only. That part we already calculate in the previous steps. A1 of 2 minus T into F2 derivative of F2 of Z, that is the what? 0.245. that part we already calculated, so same value we written here. Okay, so 0.245, W naught is 0.5 and 1 of T, and this is 1 that we are eliminated, and it's 0 1 and minus 1 is my A naught. Okay, 0 1 and minus 1.